Hi everyone, welcome back. This is class number 10, Quantitative Statistics for Research Methods. This work is an adaptation of work done by Tom Sensky. It's work that I found a while ago, and it's a PowerPoint presentation that I think really kind of simplifies a lot of the complex content of statistics while still being somewhat informative. So I wanted to just start by giving you some recommended resources that you could look at. The first two are my favorites. The first one, Statistics for Dummies. The entire Dummies collection is actually pretty cool. So you can look at that, and it fairly, it simplifies a lot of these kind of complex issues. Or Statistics for people who think they hate statistics, which would probably be 95% of the population. That's my favorite one. Also, somewhat simplifies a lot of the difficult to understand concepts, but it's done in a way that's kind of humorous. So that's a nice book. And then the other three are a little bit more in depth. So let's first talk about some types of data that we know of and the variables that we've talked about in this class. The first being quantitative or objective variables. These are usually numbers or continuous variables. The next one, qualitative or subjective variables. These would be things that you would, these would be kind of answers on a questionnaire or information from a scale that you might get. In terms of quantitative variables, there are two types. There's ratio and interval. Ratio being things like pulse rate, height. Interval explaining more of a range, in this case temperature. And on the qualitative side of the variables, there are two kinds. There's the ordinal and the nominal. The ordinal kind of defining social class would be a good example, and the nominal something defining gender or ethnicity. So the first thing I want to do is just kind of get your feet wet a little bit and get you kind of used to the nomenclature and the terms. And we're going to start with something called a normal distribution. This is this curve that you see before you is basically called a bell curve because it's shaped like a bell. You notice that it has a peak in the middle, it has two tails at either end, and then it has two shaded areas that are gray. And the mean is the average of the data that you see in the bell curve. So the mean is basically determined by taking all of the values that you've collected, adding them up, and then dividing by the number of values. Also, you can see that the cases around the mean are symmetrical. So the mean is directly right in the middle. Now that doesn't always happen all the time, but we'll talk about that in a moment. And the last thing I want you to kind of recognize is that there is a spread of data. Notice that the gray area is, is kind of far away from the red line. We call this the standard deviation, or the deviation from the mean. How far away is that data from the mean? And the reason that those areas are shaded in as gray is because anything beyond that border of gray is going to be greater than 2 standard deviations from the mean, which shows that it's extremely different from the mean. We'll talk about that in a little bit. And so that is a real important part of understanding how statistics are either significantly different or not different at all. So again, let's take a look at some of the terms. The mean is the average or arithmetic mean. The median is the value which comes halfway, or it comes halfway between the data when they're ranked in order, and the mode is the one that's most common or most frequently observed. Now, the median is often the same as the mean. In the case where the median is not the same as the mean, which we'll look at in a moment, you'll start to see a bell curve that doesn't look exactly like a bell, and I'll explain why. The mode in this case is really it's not very practical when it comes to statistics. If you're running frequencies, like if you want to see how many times this particular average or this value shows up, then you would report a mode. But in most cases, in terms of practical statistics, it's not really reported that much. So let's take a look further at the standard deviation and how to determine it. Well, the standard deviation is determined by taking the square root of the sum, so you add up all of the values, the value that you have, that you've collected, minus the mean squared. So take your value, subtract the mean, and square that number. Add all of those numbers up, and then divide that particular number by the number of values or the number of observations. Take the square root of that entire equation, and you're left with what's called the standard deviation. Now, the standard deviation decreases as a function of two things. One, a smaller spread of values about the mean, which we'll look at in a moment, and two, a larger number of values. One thing you do need to understand, though, is that in a normal distribution, about 95% of the values will lie within two standard deviations of the mean, meaning 95% of the information you collect is going to be where that green arrow is on both sides of the red line. Now, the standard deviation becomes very important because the standard deviation gives us an idea of how much variance there is in the data, how different it is when compared kind of to itself. And that gives you a lot of information, because if you have a data point that is very close to the mean or very close to the average, it doesn't show a lot of variance. However, if you have data points that are far away from the mean and close to the mean, then you do have variance. So it's important to understand the standard deviation is that first statistical term that we really look for to get an idea of how far away is this data from the average. And we're actually going to use a real-world example of IQ tests to take a look at this even further. But let's take a look at how standard deviation and sample size play a role. So when you have 10 people in a group, you'll see that there's a very large spread about the average, or about the mean, which in this case is the red line. You multiply that by 5 and take 50 subjects or 50 participants, and you'll notice that the bell curve gets a little bit more narrow. And if you triple that to 150 participants, as the sample size increases, the standard deviation goes down. So what that basically says is that for most of our studies, we want to have a sample size that's large enough so that our standard deviation is not gigantic. And that's an important point to make. Now, I had mentioned before that if the mean is not the same as the median, remember the median is the middle of those values. If the mean is not the same as the median, what you get is you get what's called a skewed distribution. So in this case, we have the mean where the red line is, but we have the median over here, which is basically 50% of the values that lie on either side of that green line. It's important to understand that when we do that, we get what's called a skew, and that skew, although not a normal distribution, also can be statistically calculated or manipulated by other kinds of tests that are not used when you have a normal distribution. So there are ways of getting at the data, but you're using different statistical methods and tests to do that. Okay, so how do we determine if a variable follows a normal distribution? Well, we can, we call this a parametric statistic. Parametric statistic is basically a statistic that's used when the variable follows a normal distribution. Statistics packages can test for normal distribution or normality, but we know that the distribution is unlikely to be normal if, number one, the mean is different from the median, which is what we saw in this skewed distribution slide. Here's the mean, and here's the median. Or if there are two standard deviations below the mean, gives an impossible answer. So again, two standard deviations below the mean gives an impossible answer, like as if height were less than 0 centimeters, which is physically impossible. So those are some criteria to follow, or some of the reference points to determine whether or not there is a normal distribution or what would be considered a non-normal distribution, or a skewed distribution in this case. And we also look at some examples. Normally distributed variables are things like height, weight, even hemoglobin, blood pressure, heart rate, things of that nature. Whereas Skewed distributed variables could be bankers' bonuses, which have a tremendous amount of variance, and therefore the mean not being close to the median. Maybe number of marriages is another example. So there are other ways to get at that data, as I mentioned before. If we look at the distribution and the statistical tests, most common statistical tests rely on the variables being tested having a normal distribution. And as I mentioned before, these are called parametric tests. However, where the parametric tests are not used, we have non-parametric tests that are applied and don't require the data set to be normally distributed. Now, also, if you have a skewed data set, you can use what's called a transformation, but this is real statistical massaging, meaning you can take the square root of variables, you can square them, you can take the log transformation of variables, and basically make them into a normally distributed variable, or make the variable into one that's normally distributed. But now what you're doing is you're kind of massaging the numbers with statistics to just be able to run a parametric test that you would run on a normally distributed variable. It's, I'd rather see a non-parametric test on data that is skewed than run a parametric test on data that you actually turned into being normally distributed. It's kind of like a little bit artificial in that sense, but people have done it. So now we kind of know how data is distributed, what it looks like. Let's take a look at a real-world example using an IQ test. So here's the example, and you've tested a sample of people with a validated IQ test, and it's been standardized on a large sample to have a mean of 100 and a standard deviation of 15. So the large sample has a mean of 100, the score is 100, standard deviation of 15, meaning it goes from 100 to 85 on the left and to 115 on the right. We take our standard deviation, which is again the sum of our values minus the mean squared over the number of observation or values, and we take the square root of that. So we get our standard deviation, and in this case, our standard deviation is about is 15. So we administer the test now to samples of 25 people, and we expect random variation of the means because we're actually administering this to groups of people over a period of time, and we're repeating that kind of administration. We're repeating that testing. So if we get this random variation around the mean, we call this the standard error. And it's important to understand that the standard deviation and the standard error, although they measure something similar, they're really defined differently. In this case, the standard error is determined by taking the standard deviation, which is what we had before, and that was 15, and dividing it by the square root of the sample size of the people who we're testing. So the sample size in this case is 25 people. We take the square root of 25 and we divide it into 15, and we're left with 3. So our standard error is 3, our standard deviation is 15. Now, let's look at the difference in the definitions. Standard deviation is a measure of variability of scores in a particular sample, meaning the sample or that you collected, the data that you got. Your standard deviation is a measure of the variability of those scores. However, the standard error of the mean is an estimate of the variability of estimated population means taken from repeated samples of that population. So it gives an estimate of the precision of the sample mean. So it is that the standard deviation is the measure of variability of your own scores, whereas the standard error is the estimate of the variability of the population against which you're measuring. Let's take a look at how this plays out. So if we have a sample of 25 people that yields a mean IQ score of 107.5, we know we're within one standard deviation because our standard deviation is 15. And that would be, one standard deviation would be a score of 115. So we're within that. What are the chances of obtaining an IQ of 107.5 or more in a sample of 25 people from the same population as that on which the test was standardized? So basically we're taking a chunk of the people who were tested and we're saying, what are the chances in a sample of 25 of those people that you would score either a 107.5 or higher on an IQ test? Well, let's take a look. So we have to determine how far out the sample IQ is in the population distribution, and we calculate that as the area under the curve to the right of the sample mean, in this case to the right of that green line. We basically take the sample mean, which was 107.5, which we looked at, minus the population mean, and we divide that by the standard error. So we're basically dividing 7.5 by 3, and we get 2.5. Now, what is 2.5? 2.5 is the ratio that tells us how far out on the standard distribution we are. The higher the number, the further we are from the population mean. So the further we are from the population mean, it means that your particular sample of 25 people who were tested against a population that scored an average of 100, it's basically saying that your sample is significantly different from the general population that scored 100 on their IQ test. So, if we look at the area to the right of that line, of that green line, we're basically saying, and this is using a table, but there are ways to do it, to calculate it, but in this case we're using a table. We're going to say basically that there is a 1 in 160 chance that the sample mean, meaning your sample of 25 people, came from the same population on which the IQ test was standardized, where the actual score was an average of 100. So, what does that really say? Okay, well there's a very small chance, it's 1 in 160, that the sample mean came from the same population that the IQ test was taken from. We call this a p-value, and the p-value stands for probability, the probability value. So traditionally, we say that something is significant or is significantly different than the population mean if it has 1 in a 20 chance or less of coming from the population in which the test was standardized. So again, in this case, we have a 1 in 160 chance. That means, if you look back, that p-value is 0.006. There's a very, very small chance that this came from the population mean, meaning that there's a huge difference between the people who scored 107.5 and 100. Very small chance that those people came from the average. They're much different than the average. That's basically what it's saying. But we use, by convention, by tradition, we use a 1 in 20 chance or less. Basically saying, look, if these scores of 107.5 are due to chance, there's only a 5% chance that it's due to a flip of a coin, or what we call chance. I hate to use the word chance again, but basically saying there's only a 5% chance that it's due to the flip of a coin. It's 95% that the reason 107.5 is where it is because it's statistically significantly different than that 100, which is the average of the population. So in this case, our sample had a significantly greater IQ than the reference population because the p-value was so small. There was such a small chance that the 25 people you tested that are just past that green line came from the general population. All we're looking for is a 1 in 20 chance. In this case, we saw a 1 in 160 chance. So we'll look at how that p-value also speaks to not only statistical significance, which in this case, this is what we're looking at, but also clinical significance, real-world significance. Now, let's say we take our sample mean, our green line, and we move it. We move it closer to the red. If we move the green line closer to the red, we look at the area of distribution to the right of the green line, and we see that that area really increases. Again, take a look at the green line, and we move it and you see that the area goes up. Okay, so now what we're saying is we're just going to eyeball this. We're not even going to do any kind of calculation, but we're basically going to look and say, all right, well, there's a very, very small percentage of people who are in this little space to the right of the green line, but there's a much larger percentage of people who are in the space to the right of the green line in this example. So what we're looking at here is just take a look at how the green line moves to the red. As the green line gets closer to the red, it means that the sample that you collected the data from, which is the green line, is very close to the average. In this case, 103 and the population mean of 100. So again, your 25 people scored 103 on their IQ test. The population mean is 100. Is that statistically significantly different? Chances are probably not. But again, it depends on how many people you've tested. In our example, you've tested 25. What if you tested 25,000? Then the more people you test, the smaller the difference you need in order for that to be statistically significant. And that's kind of an important point here. And I'll show you that in a table in a moment. But the more people you have in your sample, the less of a distance from the population mean you need in order for it to be significant. Okay, so now let's take a look at how we compare two samples. And we'll come back to the IQ example in a moment. Here we have two samples. We have the pink sample with a red line and the blue sample with a blue line. And pink is sample A, and there's our mean right in the middle. And blue is sample B, and there's our mean right in the middle. What you should notice right away between these two samples is that they are not overlapping. Is that basically because they are not overlapping, they are very likely to be different. And this can be anything from measuring height and weight in two groups, or it could be pulse rate, it could be blood pressure, it doesn't matter. You have a difference here in the two groups. Let's go back to the IQ example. Now we have, again, our two populations, the pink one and the blue one. In the pink one, we have a mean or an average score on an IQ test of 100. In the blue one, we have a mean of 110. Notice where your sample falls at 107.5. Actually falls a little bit closer to the mean of 110 than it does to the mean of 100. Okay, so what we say is we probably think that the 107.5 came from the population that scored an average of 110 rather than the population that scored an average of 100. Now, we basically assume that the sample came from the original population, which is where the mean is 100. However, if we test our null hypothesis and we say, wait a minute, the IQ test that we saw, the average was 107.5, it looks like maybe it's not significantly different than 100. That's our null hypothesis, basically saying there's really no difference between the general population mean of 100 and 107.5. But if we look at the area under the standard population curve to the right of our sample, look at how small that is. That represents the likelihood of observing the sample mean by chance under the null hypothesis, basically saying that our sample that had an average of 107.5 comes from the standard population with an average of 100. Would you agree? I wouldn't, because I think there's a very small chance that those people who scored 107.5 are coming from that pink side, that average of 100 population. Or I should say the population that scored the average of 100. Now, that is what I'm asking you to focus on. That little tiny sliver right there is basically telling us what chance there is of our sample mean coming from the original population where the score was 100. We call this an alpha level. And again, it's a way of describing what data are we seeing by chance and what data are we seeing as a result of it being a significantly different score than what comes from the general population. The alpha level is often set at 0.05. Again, just to reiterate, saying that there's a 5% chance that this is due to a flip of a coin and a 95% chance that this number, 107.5, is statistically significantly different than the average of 100. Now, if the sample comes from the standard population, then we expect to find a mean of 107.5 in about 1 out of every 20 people tested. Chances are that's not going to be the case. Now, we can also conceptualize the alpha by seeing what happens if we move the sample mean, just like we did in the other example. But in this case, now you have two populations that you're working with, one with an average of 100, one with an average of 110. In this case, the sample mean, or the green dotted line, is closer to the red population, and basically eyeballing it, you would probably say it's so close to the red population mean that there really isn't much of a difference there. The area under the curve, just like we looked at last time, is larger. So that means that there's not this 1 in 160 chance, but there's a 1 in 15 chance that the green dotted line is coming from the general population, where the average score is 100. The larger the alpha, the greater the chance that the sample comes from the red population. Remember, the alpha is set at 0.05, saying that there's a 5% chance that it's the flip of a coin, a 95% chance that there's a true difference. What if we raise the alpha to 0.10? Then what we're saying is there's a 10% chance it's due to the flip of a coin and a 90% chance that it is significantly different from the general population. What if we raise the alpha to 0.25? We're saying there's a 25% chance it's due to the flip of a coin and a 75% chance that it's different from the general population. You see what I'm getting at? The larger the alpha, the greater the chance that the sample comes from the red population. Now, if you're doing research, you probably want your alpha level to be set at 0.05 or lower, because what you want to find is you want to find a almost beyond the shadow of a doubt that your numbers are significantly different from the original population. So the alpha level represents the probability of finding a significant difference between two means when none exists. So again, the none exists really has everything to do with the null hypothesis, right? In the null hypothesis, you're saying that the score of 107.5 is not statistically different than the score of 100. You want to reject the null hypothesis in your research. So basically what you're saying is, I'm going to set the alpha level as low as I possibly can to basically say, hey, look at that. I found a difference even though none exists, or it looks like none exists. This is known as a type 1 error. And we'll talk about this in a little bit. We'll summarize it in a moment. So the area under the other population curve, the blue curve to the left of the sample, looks pretty large. It actually looks like a bigger area than we saw before in the red curve. And it represents the likelihood of observing the sample mean by chance under the alternative hypothesis, basically saying that the 107.5 actually comes from the other population that has an average score of 110. Now, this is the area I'm talking about. So what we're saying here really is that a score of 107.5, taking everything that we've said before, is statistically different than the population that has an average score of 100. However, it is not statistically different than the population that has an average score of 110. And again, you should be able to see how the area under these curves kind of dictate the chances that the 107.5 is either much greater or statistically significant from 100 or statistically significant from 110. Again, you can definitely go over this presentation. There's a lot to digest here, but by looking at the areas under the curve, it should become clear how those are the components of this particular graphic that dictate the statistical significance. Now, when we look at this in reference to the alternative hypothesis that our sample comes from the other population, we call this the beta level. And this is normally set at 0.20. Now, when we set these things like 0.05 and 0.20, we're basically saying, look, before we do our research, we're setting these values because we're very confident that we're going to be able to reject the null hypothesis, and we're very confident that we're going to have a power that's greater than, or a power of roughly 80% in our study. That's what the beta has to do with. It really has to do with power and magnitude of the study, whereas the p-value has to do with whether or not the variables that you're measuring are statistically different than an original population or a standard population or whatever it is you're measuring against. Now, we look at the beta level as representing the probability of not finding a significant difference between the two means when one actually does exist. So it's kind of the opposite of the alpha level. We call this a type 2 error when we see that there's a high probability of not finding a significant difference when one exists. And we really attribute this to an inadequate sample size. And here's a really good example. So if the population sizes are reduced in both our pink and our blue population, we notice that the standard error increases because the spread is much, much greater. And also the beta increases. So the probability of failing to find a significant difference between the two means is enhanced. This increases the likelihood of a type 2 error. And you don't really want to have a type 2 error because if you do, chances are you're telling your readers when you publish your information, hey, I didn't have enough people in my sample. However, if you're committing a type 1 error, chances are you've set your alpha level probably too high and you're not finding a significant difference even though one exists. So again, these are ways of looking at the errors between measuring your variable or your data versus a sample population. Let's take a look at how we define these. A type 1 error is known as a false positive. It's when we find a significant difference even though one does not exist. We usually set our alpha level at 0.05, basically saying 5% of our differences are due to chance. However, a type 2 error related to our beta is a false negative. So we think it's negative, but it's actually false. So there is a significant difference here, but we can't find one because our subject pool is so small. We set this at about 0.20, and we subtract the 0.20 from 1, getting basically a fraction, and the beta is usually 80%. You're usually shooting for 80%. What that really means is that your sample size is large enough that the power, the magnitude of your study is set at 80%. So for instance, if you have a 30% power, your study is underpowered. Often that happens when you have too small of a group. If your study is 50% powered, it looks like your group is somewhat large enough, but maybe you could even get more people to be in your study and increase the power, the magnitude of your study. And if your power is at 80%, it means that you have just the right amount of people in your study. So below it says the power is related to sample size. The larger the sample, the smaller the standard error. And there's less of an overlap between curves. Once there's less of an overlap between curves, it means there's a bigger difference between the two populations. And therefore, the power is actually much higher. So doing power calculations, we're not actually going to do those, but we do use the alpha level, we use the beta level. We also have to have an estimate of a standard deviation and the difference that we're going to find in the sample means. And that will give you the smallest sample size you need to avoid committing a type 2 error, meaning that even though significance exists, you should be able to find it if you have enough people in your group or your groups, depending upon what kind of research you're doing. So we use power calculations before we do any kind of research to determine how many people we need in each group. And it's intended to estimate the sample size, and you can apply a standard formula that is used. And basically you have a few requirements in order to determine power. One is a hypothesis, the other is a measure or an estimate of variability of what it is that you're looking to measure, the outcome, and the other is the difference between your groups. So you need to have an idea. Now, how do you go about doing that? Well, you can go back to previous work that's been done in your area and try to determine, what the differences are between those groups and see if what you're measuring is going to give you a similar difference. It's hard, it's not easy to determine the variability, but if you have some work that's been done in the past in what it is you're studying, you can get a very good idea of how many people you need in each group. Rule of thumb is about 15 in each group. However, that doesn't always work out. Let me show you why. Now, we talked about the p-value as being something that indicates statistical significance, but statistical significance does not necessarily translate to something that is clinically significant, meaning significant in the real world. So let's take a look at some of these examples. A sample size of 4, population mean, or the original average of the original population average was 100, and the sample mean was 110. In this case, statistically significantly different, right? But now, if you go down a couple of rows and look at a sample size of 400, look at the difference between the population mean and the sample mean scores. It's only a score of 1. That's the difference, and it's still statistically significantly different. Now go down to 10,000 people in your group, and you've got a population mean of 100 and a sample mean of 100.2. Now it's a difference of 0.2. Also statistically significant based on the p-value. So basically what this is saying is the more people you have in your group, the less the standard error and the less of a change you need to see in your sample mean versus the population mean in order for it to be statistically significant. But let's take a look at what some authors have said really constitute clinical significance. One is a large proportion of patients improving. And this is all kind of from the clinic, but this also relates to athletes. It relates to subjects. So if you have a training program or a training study and you see improvement, it's got to be a large proportion of those people who are improving to actually have significance in the real world. A change which is large in magnitude. So the power of the study needs to be very high. And you need to see that not only is there a large proportion or percentage of patients improving, but the improvement itself is huge. An improvement in patients' everyday functioning. Again, this could also be related to athletics. So everyday functioning or a specific task, a specific sport, whatever it is, being able to see a large improvement in that might have real-world practicality. Reduction in symptoms by more than 50% or more, and that would be a little bit more related to the clinic. You might also see an improvement in performance, let's say performance-enhancing drugs or things of that nature related to athletes or sport, an increase by 50% or more might indicate that there's real-world significance there. Elimination of a presenting problem is also something else to look into. So these are ways of determining whether or not data actually has real-world practicality. Now, let's take a look at how we measure clinically significant improvement. We have an abnormal population here, which is not to be confused with a non-normal distribution. Here's the distribution of the dysfunctional sample. And we have our gray areas, which are the areas that are beyond 2 standard deviations above the mean. Now, we have a cutoff here, which is the border here of the gray shaded area. And this first possible cutoff is anything outside the range of the dysfunctional population. So if we see that there is something that is greater than 2 standard deviations from the mean, then we're probably saying there's a statistically significant difference there. We're going to superimpose right now a normal population on our abnormal population, keeping our first cutoff intact. And we see that the blue is the distribution of the normal or functional sample, and we have a second cutoff. Now that second cutoff really relates to the blue but it's actually right in the middle of our abnormal population. And that's kind of an interesting point. It's within the normal population, but it is kind of splitting the abnormal population in half. And we have a third cutoff here, which is more within the normal than the abnormal range. All of these would be cutoffs to determine whether or not data is clinically significant. Again, you can look back at this and take a look at how these lines relate to each bell curve. But basically what you're looking at is anything greater than 2 standard deviations, or anything that splits both curves in half. And again, looking at the area under the curve, you can see that they're quite small for the A and B. For the C, they're a little bit larger. So finding your data in any of these kind of ranges would give you an idea of measures of clinically significant improvement. Okay, so we're going to move on a little bit to tests, different tests that we do and that we focus on. First one is called an unpaired or independent sample t-test. And we look at 2 distributions that are widely separated, so their means are clearly different. That's on the top line. And then if the distributions overlap, it becomes unclear whether the samples come from the same population. So this is what I want you to think of. I want you to think of heart rate, and I want you to think of 2 measurements of heart rate, basically saying that we have a heart rate on average of 80 and a heart rate on average of 100. And we're measuring the study is looking at the effect of a new device that is supposed to be a calming device, and it's sold at Brookstone, and we're doing a study on it to determine whether or not over 10 weeks it reduces heart rate. But we have a heart rate of 80 and a heart rate of 100. First thing we have to do is we have to kind of equalize those groups. We can't really say there's a reduction unless we use a relative percentage of where the individual started, whether it be 80 or 100, and then what the decrease or what the increase was from those numbers. That's a possibility. But in this case, what we want to do is we want to see the measure of the difference between the sample means, in this case 80 and 100, in relation to the overall spread. So what we look for is something called a t-score. We look at the difference between the means, and then we look at the standard error of that difference. We divide the difference of the means by the standard error of the difference, and we get what's called a t-score. So, first thing is we have to get the standard error. That is taking the standard deviation and dividing it by the square root of the sample size. Now, with a smaller sample size here, we know that the standard error will increase, and as does the overlap between the 2 curves. In the case of the second example here on the lower line, the t-score will go down. The reason is because there is more of a standard error, and if you're dividing the standard error of the difference here by the difference between the means, and you have a standard error that's larger, if you're putting a larger number into a smaller number, you're going to end up with a smaller number. Therefore, the t is going to decrease. We're going to see in a moment how that will change. If we represent now the previous IQ example, in the IQ example, we assessed whether a particular sample was likely to have come from a particular population. If we had 2 samples rather than a sample just plus the population, so basically 1 sample we were measuring, we would then compare 2 samples using an independent sample t-test to determine what's basically the same about these and what's different. But again, what you should understand is that going back to this, the smaller the sample size, the larger the standard error, and the smaller the t-score. We'll come back to that in a moment. Now let's take a look at comparing 2 means from the sample using a paired t-test. And again, shows how the t-score changes using the independent, but also how the t-score changes using not a dependent, but it's known as a paired t-test. So in this case, we have 4 subjects, and we have 2 columns, okay? And let's say column A happens to be weight training, and column B happens to be a control group, okay? And these are the various scores here. You'll notice that the control group scored better on whatever it was we were measuring in every case, in every subject's case. So assume that the A and the B represent measures on the same subjects at 2 different time points, okay? Note the variation between the subjects is actually is actually wider. So between the subjects, meaning 10 and 0 and 60 and 27, 11 and 3 and 65 and 31. There's a huge range between these numbers here if you're looking between subjects. But look at within subjects. There's a very small increase, 10 to 11, 0 to 3, 60 to 65, 27 to 31. So there's not a lot of variance in the rows, but there is a lot of variance in the columns. So if we were to treat this as an independent t-test, we would be testing basically the columns here. And just testing, we'd be testing the rows here. And that would basically give us a very small t-value. The reason being is we have a very small subject pool and we have a large standard error, which is basically going to decrease our t-score. Decreasing our t-score will also decrease the probability that these groups are statistically significantly different. However, if we treat the values as paired t-test, meaning we actually look at not the rows, but we look at the columns, meaning we take the means here and we look at the difference between the mean of this number in column A and the mean of this number in column B. Then what we're dealing with is, going back here, we take the difference between the means and divide it by the standard error of the difference. Now, the difference between the means is a huge number. Even if the standard error is large, we're still going to get a t-value that's much higher than if we treated both columns separately. And therefore, with the t-value being higher, the probability of there being a statistically significant difference between these two groups is much greater. You haven't changed the number of subjects. All you've done is you've changed the way that you're looking at the data. Instead of looking at it in rows, you're actually looking at it in columns. We call this a paired t-test because these groups are now paired, because we do this usually when there's a pre and post type situation. So understanding this in terms of a definition, one sample or independent sample t-test compares means of two independent samples, whereas a paired t-test is used to compare two repeated measures from the same subjects, usually considered a pre and post. Now, this is if we have two groups. What if we have more than two groups? Well, we do something called an analysis of variance, and the acronym is ANOVA. And in order to determine an ANOVA, what we're trying to do is we're looking at the variance or the differences between groups and also within groups. And I'll show you that in terms of a graphic in a moment. But in order to get an idea of whether or not the ANOVA is the right test and whether or not our data is statistically significant, we look at the measure of between groups difference or variance and the measure of within groups variance or difference, and we divide the between groups by the within groups. We come up with what's called an F statistic. Now, the fact is I've been speaking for almost 48 minutes, and I'm absolutely positive that F means something different to you than it does to me right now. But let's focus a little bit more on the statistics for now. So the greater the F statistic, the more significant the result. The value of the F is in standard tables, but I'm also going to show you how we determine it. Let's look at this graphically to make it a little bit more sense. Here we have three groups. We have a resistance training group in pink, we have a resistance training group in supplement in blue, and we have an aerobic training group. And we're looking to see which one of these increases one rep max the most after 10 weeks of training. So what we have is we have a within group variance, which you see is basically equal for all the groups, but we have what's called a between groups variance. Look at the groups. The means are completely separated. Right? The orange line, the blue line, the green line, huge difference between these groups. Now, the between group variance is large relative to the within group variance. So the F statistic is going to be very large, which pretty much means there's going to be a significantly different set, or there's going to be a statistically significant difference here between orange, blue, and green, which maybe tells you a lot about your data and about your study and about your training. Let's look at this a different way. Here we have the within group variance, which is, somewhat large, and it's the same for the pink as it is for the blue as it is for the green, but take a look at the overlap. There's not a huge between group variance. So now when we divide the between group variance by the within group variance to get that F statistic, we're going to see an F statistic that's smaller and therefore probably no significant differences between the groups. So what are we saying here? Well, in this case, we're saying that there's a huge difference between resistance training and resistance and supplement training and aerobic training in performing 1 rep max after 10 weeks of training. And in this example, we're saying there's not much of a difference. Doesn't really matter what you do. Your 1 rep max is basically not improved no matter what kind of training you do over 10 weeks. Again, it of course depends on what your data looks like, but this gives you an idea of how more than 2 groups kind of relate to one another. Now, if we look at an example of an ANOVA and how it plays out, and this is kind of a boring example, but participants asked to rate DVD players, we can see the age groups here on the left, the number in each age group, and here's the total number of subjects tested, the mean score on a scale for each age group, and then the mean score across the board, and the standard deviation in the same fashion. So we call this a one-way ANOVA, and what we get basically is we get this kind of chart, which is the sum of squares. So we square every single value, and we get the sum between groups. So between groups, okay, here, and then we get the within groups. So we get the same thing, right? Sum of squares for both the between groups and the within groups. And then how do we get our F statistic? Well, we take the between groups mean square here, and we divide it by the within group's mean square, and we're getting that from this data here. We divide this by this, and we get an F statistic of 4.60, which leads us to say that there's a statistically significant difference between these groups. There is not one, however, within the groups. So, between group sum of squares concerns the variance or the variability between the groups. The within group sum of squares is the variance within the groups. Again, just going back to this, between the groups in the columns, within the groups in the rows. Okay. Now let's look at what else we need. We also have something called degrees of freedom. That represents the number of independent data points required to define each value calculated. So in this case, if we know the overall mean, once we know the rating of 67 respondents, we then can work out the rating given by the 68th. Hence, the total degrees of freedom is n, which in this case is 68, minus 1. And it usually is in that case. So we know the ratings of 67 respondents. We're then able to work out the rating given by the 68th. If we know the overall mean plus the means of 5 out of 6 groups, we can then calculate the 6th group. So again, we have an n of 6 groups minus 1, and we have a degrees of freedom of 5. We then take the total degrees of freedom here, and we subtract the degrees of freedom of between groups, and we get the within groups degrees of freedom. Now, why is that really important? Well, it's really important because the degrees of freedom represent the number of independent data points required to define each value calculated. All we need is 62 data points here. All we need is 5 groups here to define the values calculated. All we need is 67 subjects total to define the values calculated. That's all that's saying. And it's part of the report. When you report this information, mean scores of total DVD assessment varied significantly between age groups. Here's your F statistic of 4.60. In parentheses, you put in the group degrees of freedom, or the between group degrees of freedom, and the within group degrees of freedom, and then you follow it by the p-value. That is the proper way of actually reporting it. And they determine the degrees of freedom will determine the significance of the F statistic. Now, if this became 62, where it was 68 minus 6, then this F statistic would be lower, and the significance would actually be lower as well. Or I should say, the significance would be higher in this case. My fault, because you have less of degrees of freedom. You have basically less groups that would be needed to define the independent values, and less groups would mean that it's not as significant. more groups to define those independent values would indicate that it is highly significant. And in this case, it's a lot lower than 0.05. So in a summary, if we have continuous variables with two groups, we do an independent t-test. With more than two groups, we do an ANOVA. If we have continuous variables in the same sample, like a pre and post, we do a paired t-test or matched pairs t-test, and a repeated measures ANOVA, we can do that as well because it just repeats the measure over and over again if you have more than two groups. Categorical variables, we can use what's called a chi-square test with two groups. We can also do that with over two groups. And if we have non-parametric data or data that's not normally distributed, we do what's called a Mann-Whitney U-test or median test or a Kruskal-Wallis test if we have more than two groups. But again, those are not tests we're going to go over today. Test of association, correlation, used to investigate the relationship between two variables consisting of interval or ratio data. And these indicate whether there's a relationship, the direction of that relationship, and the strength. So let's take a look at an example. Here we have 24 people with rheumatoid arthritis. We have the hospital anxiety and depression scale here, and the suicidal intent scale here. And we're basically looking to see whether or not depression levels linked to or associated with suicidal intent in people with rheumatoid arthritis. Well, let's take a look. The correlation is 0.34, and it's moving in the opposite direction. It's kind of a negative correlation. It basically states that with greater depression, there's less of a chance that you're going to have suicidal tendencies. With more depression here, with less depression here, it looks like you're going to have more suicidal tendencies. So that kind of doesn't really make that much sense. So basically, we're just saying that there really isn't a major correlation here. However, the red line here is drawn through the data called the line of best fit, and basically it is the mean of all of these data points. You see there's data point x1, x2, x3, x4. Notice x1 and x2 are quite far from the red line or the mean, whereas x3 and x4 are quite tight to the red line. So because deviations can be either negative or positive, each one of these deviations is squared, and then the squared deviations are added together, and the square root is then taken, and that's how we determine the actual correlation. It's important to understand, though, even with 24 subjects, you still have most of this data is around the mean. So it basically means that aside from these what's called outliers, or the ones that kind of sit far away from the mean, this is basically giving us a true statement saying that that depression scale scores don't really relate to suicidal intent in people with rheumatoid arthritis. Now, let's take a look at another sample of people with coronary artery bypass. These are 87 people. Again, the sample size is larger, but take a look at the correlation. It's much, much lower, basically saying there is no association between depression scale scores and suicidal intent. Here, at least, you see a pattern on the left. Here, there is absolutely no pattern. Let's take a look at what some patterns look like. In a positive correlation, you have the data moving from the lower left to the top right. In a negative correlation, you have it moving from the top left to the lower right. And then when there's no correlation, the data is scattered all over. And this is looking at hours of studying versus grades. Sorry, that's backwards, but hours of studying versus grades. And you can see that the more hours we study, the higher the grades. Here, hours of watching TV correlate to lower grades. Lower the grade, the more we watch TV. And in terms of hours of gardening, that doesn't really have to do with grades at all. This gives you an idea of other correlations and how the coefficient is then reported based on the data. This is a complete scatter, and there is no correlation here. This correlation actually is moving from left to right and looks like it's about 0.40. Also, to give you just a little bit of a reference point, a perfect correlation, positive correlation, is 1.0, which you kind of see over here. 0.95 is actually quite large, and that would be like intensity on the bottom and heart rate on the top. As intensity goes up, heart rate goes up. So that provides a really strong relationship. Whereas negative correlations at 0.95 at the same rate show that as we do, let's say, like the step test. So as we increase our heart rates here, we see an increase in, as the heart rate is higher here, there's a lower VO2 max. When we do our step test, basically the higher the heart rate after the step test, when it's measured 5 seconds after the step test has been completed, there's a lower fitness level. So the idea is to bring your heart rate down low, and you would see a much higher fitness level. So again, this could be heart rate after 5 seconds, this could be fitness level, and that shows a negative correlation, and it's actually quite strong. The other ones are kind of in the middle, 0.60, 0.80, 0.70 negative, 0.90 negative. So again, this just gives you an idea of the relationship of the data and what it says about them. So our next slide shows a table which gives us an idea of what the correlation would need to be with a particular number of people in your population, and then how that relates to the probability level or the p-value. So let's take, for instance, if we look at these black bars here, anything within the black bar being 10 people in your population to 50 people in your population, you get a sense of what the correlation would need to be, and then what that p-level or level of significance would be. So if we're looking at 0.05 and we move down and we have 30 people in our group and we're looking at a 0.05 alpha level or probability, we probably need a correlation of somewhere around 0.35, or roughly a third of the data is, a little bit more than a third of the data shows a strong relationship. Whereas if you had 10 people in your group, you'd need almost a 0.6, or almost 2/3 of the data shows a positive relationship. And then if you have 50 people in the group, you would see it's almost a quarter, a little bit more than a quarter of the data has to show a positive relationship. So basically, the lower the number of the people in the group, the higher the correlation would need to be at the same alpha level or probability level. Now, what are some of the problems with correlation? Well, one is it doesn't by itself demonstrate causation. Causation implies correlation, but correlation does not imply causation. It's basically said that correlation is more a definition of a causal relationship, but not a causal relationship. Also, there's a third or lurking variable problem. This may be often difficult to uncover and has to do with outliers that sit very far from the mean. There might be a directionality problem. Does variable A cause a change in variable B, or is it the other way around? And it may be unstable in small sample sizes. As you noticed, you have to have a very, very high correlation when you have small sample sizes. There also may be spurious results with larger samples. So you may be making a statement with large samples that's not necessarily true. However, in the correlation table, it looks like it might be. So be careful about how you report your information. Now, regression analysis is a little bit different, also related to correlation, but this determines the magnitude or power of a relationship and predicts the effect of one variable on another. Also allows the identification of the effect of a change in the independent variable, which is on the x-axis, what that changes on the dependent variable on the y. So let's take a look. If you look at this height versus age linear regression, you see that on the x-axis, age in years from the age of 4 to the age of 12, and then you see height in centimeters from 95 to 155. And what this data is showing you is a very positive relationship that as somebody ages from 4 years old to 12 years old, they increase in height. Now, there are some outliers here. There are some kind of data points that sit pretty far from the mean, but most of these data points surround the average line here. So it really shows a nice and strong positive relationship, and also it shows predictability. As we get older, we get taller. Let's step back for a moment and take a look at how people actually torture data, meaning how they basically tend to manipulate it, and what the pitfalls might be for that. Well, first you have to look at Are the reported findings a result from testing a primary hypothesis, meaning the hypothesis that you came up with before you started the study, or is it a secondary hypothesis? Even it could be actually before you came up with the study, but was it done before the data were analyzed? It's very important that you don't just analyze data and then come up with a hypothesis to fit the data that you just analyzed. The whole idea is to come up with a hypothesis, get the data, take the data, and analyze it, and then come up with your results. So don't try to fit your hypothesis to the data once the data has been actually collected and analyzed. Was the rationale for excluding various subjects from the analysis truthful? In other words, was there a kind of a systematic way of not including subjects in your subject pool? Either they withdrew, you withdrew them from the study. There's so many different reasons why. Or if you have data that is not very favorable, are you not collecting it? So be very careful of how authors report on their data. And were the following determined before looking at the data? Definition of exposure. So how much exposure did the data actually kind of experience? Like, in other words, did you go through the entire procedure? Was that procedure defined? Were the methods defined? Definition of an outcome. So what do you consider an outcome? What is it that you're looking for in terms of your data? What are you looking what are you looking for in terms of a change, and where are you looking for that change? Are the subject groups analyzed, and were the cutoff points defined for positive results? Also, how many statistical tests were performed, and was the effect of multiple comparisons dealt with appropriately, or did you just throw pasta up on the wall to see what stuck? That's really important as well. Are both p-values and confidence intervals reported? And have the data been reported for all subgroups and at all follow-up points? That's also an important point. Now, we understand that there's a lot of different ways to test data. There's a lot of different statistical methods we use. Obviously, there's a lot of things we look for, and there are ways to torture data as well. Let's look at how we actually report it. In correlations, we report the R value, and we report the probability value, or the p-value, and the effect size. And the effect size is more related to the power of the study than anything else. In t-tests, we report the test statistic, the degrees of freedom, the p-value, and the effect size. Although in some t-tests, we don't necessarily report the effect size, but the other ones we do. In an ANOVA, we report the F statistic, the degrees of freedom, and the p-value as well. Wilcoxon, Mann-Whitney, and Kruskal-Wallis are tests that are used for non-parametric data, so you report the test statistic and the degrees of freedom and the p-value. A chi-squared is used for categorical variables, and we report the test statistic, the degrees of freedom, and again the p-value. So these are just different ways of reporting our information. Obviously, there are many, many more statistical tests that we can use, but these are the most common. So now, how do we present the statistics? Well, we can do it in tables and graphs. And in tables and graphs, we're dealing with scaling and labeling and also redundant information. Let's kind of talk about that in a moment. So here we have line width statistics. Here we have males who are, let's say, 70 centimeters or close to that, and females who are just above 60 centimeters. Now, it looks like there's really no difference between the two bars in the graph on the left. However, if you change the scale from 0 to 100 to now 59 to 69 with less information between each tick, you're looking at the males at 68, which is basically exactly where they are on the graph on the left, and the females at 62, which is exactly where they are on the graph on the left, but look at the difference between the two bars. Here you're showing a gigantic difference, whereas if you change the scale, you're not. The only thing I would say is that your scales need to be consistent. And if they are consistent and you're reporting that information and you run the statistical test to determine whether or not there's significance, then I think you're okay. But try not to lie with the graph just by changing the scale. Another example. Here is something that's showing a trend in the data. This is actually a comparison of equilibrium scores before and after a 25-kilometer run. Again, the significance is quite high. You'll notice these little T-bars here. Those T-bars are indicating the standard deviation. And the asterisk, or the A, above that little line indicates that there's a significant difference between the white bar and the black bar, specifically under that line. This is very nice. It shows you in different sensory conditions, which are on the x-axis, 1, 2, 3, all the way through 6, how there's a trend of equilibrium score and how it goes down. Also, how the pre-run relates to one another through the sensory conditions and how the post-run relates to one another through the sensory conditions. So you're really using a nice figure here to show how the pre-run and the post-run relate to one another in each sensory condition and the trend throughout the sensory conditions 1 through 6. So this is a nice way of using a bar graph. Figures should always be relevant, and we can also use line graphs if we want for a contiguous variable. So if you're looking at like changes in temperature or changes in terms of time points, you can use a line graph, and that's always a nice way to show things. So here's a line graph looking at 3 stances on a foam surface for each testing session, 1 day post-injury through 5 days post-injury. Basically this was looking at concussive symptoms and how individuals would obtain their balance after 1 day of injury versus after 5 days of injury. And again, here on the x-axis, you've got D1 through D5. You can see that the control group shows really no change at all. It shows that their equilibrium or their error score has not changed, whereas the people who had a mild head injury show that there's a decrease here. And this is a nice use of a line graph showing how these things improved over time. We can also use a table. Tables can get very, very difficult to read. They can be very messy. However, this is nicely done. Again, the mild head injury versus the control, day 1, day 3, day 5, very nicely delineated. And here are the error scores here. The mean plus the standard deviation, day 1, day 3, day 5. And you can see how the stance and the surface relate to each one of these groups on each of the days. So this is a really nice way of comparing values and taking complex variables and measurements and really laying them out nicely. Try not to use a table to show relationships or trends. Actually, rather use either a bar graph, or you can try to show a line graph if it's relationships, but this is most likely used after a pre and post. And tables also may have a title or a legend as well, but they don't often. They have a title here. This is the title here. Error scores mean plus or minus SD by day post-injury for test and surface. And then, of course, total error scores here. The legend is not often seen. You may see a legend on the bottom of a table, which indicates if there's an asterisk, that's where they saw significant differences. That's a possibility. Or there may be acronyms that are then defined under that. So we spoke a lot about statistics, about different tests. We're going to finish up by looking at common mistakes. First is choosing the incorrect test. Make sure that when you choose your statistical test or method that it's appropriate for the data you're collecting. The second is inputting the data in an incorrect format. Make sure that you're coding your data correctly. You're putting it in the right format. So in other words, if it's currency, it's got to be currency. If it's a percentage, it's got to be a percentage. If it's a particular number, it has to be put in the right format. Even a decimal point can screw up all of your statistics and your data. So be careful. Don't misinterpret the p-value or make a type 1 or type 2 error. So try to, number one, I think primarily you really want to have enough people in your group that a significant difference is really what you're seeing. You don't want to try to say you're seeing something when you're really not seeing something. So try to have adequate numbers in your group. Decide on a level of significance after conducting the statistics. That's a big mistake because you really want to do that beforehand. To do it afterwards is kind of cheating. So you don't want to look at your data and then say, oh, well, my data is not that great, so I'm going to change my level of significance to be an alpha of 0.10. Hey, look at that. It's below 0.10. You really want to be kind of truthful to yourself. Set your alpha level and your beta level before you run your tests. Okay, that was a lot of talking. I know you guys have been listening for a while, I really appreciate it. This is probably the most lengthy presentation that I'm going to do. Any questions, please feel free to email me, and I look forward to speaking to you next time.